He is a Schrödinger Fellow from the University of Geneva, and he collaborates with Professor Nicholas Gisin, of whom you may have heard, and he will represent the group in Geneva. He will speak about recent results on indeterminism in classical mechanics and its consequences for relativity and a possible open past, and illustrate this by comparing several quantum paradoxes and showing that they are in fact paradoxes of indeterminism, not specifically quantum. The title of his talk is Potentially Realism, Classical and Quantum Indeterminism. We're very happy to have you with us, Dr. Del Santo. The floor is all yours.
Thank you very much. Thanks for the invitation and for the kind introduction. Indeed, the work I'm going to present today is kind of a long-lasting now project that we have been with Nicolas Gisin at the University of Geneva for several years, where we're having so you know that there is certain problems of this quantum certain conceptual problems of quantum mechanics, and many people are trying to understand what are the real problem of quantum mechanics as compared to their classical counterparts. So usually, for instance, with Bell's inequalities, one wants to find where the actual distinction lies, for instance, in terms of non-locality and so forth. So what we're trying to do here, the overall aim of this project instead, is approaching the problem from the classical counterpart. And I will in a moment clarify what I mean. So just keep in mind that the aim of this presentation will be to pin down how much can we push classical mechanics to get closer to the problems of quantum mechanics, and in doing this, we will try to understand what quantum mechanics, what is really quantum in the quantum mechanical problems. All right, let's start. So, classical physics, we have all studied in our undergrads that classical physics is a fully deterministic theory. What does it mean, being a fully deterministic theory, or why this thought came about? Because classical physics in general, not only Newtonian mechanics, but also fields, electromagnetism, for instance. If we take a physical system, the state of the system, so the maximal and complete information about all the relevant degrees of freedom of the system are encoded into a state. And the state is supposed to be, if it's a mechanical state, for instance, in this case, to be, you can represent it as a mathematical point, so a dimensionless point in phase space, mathematically represented by an n-tuple of real numbers. And then you have a set of dynamical laws in the form of ordinary differential equations, in the case of Newton's equations, for instance, but there's also partial differential equations in the case of waves. And then the state being a precise mathematical point, when you feed it to this machinery that is the dynamical laws, uniquely gives you a continuation in time ad libitum, in the past and in the future. So there is the uniqueness of this trajectory that is determined by your initial conditions plus the dynamical laws that forces us into understanding that classical mechanics is fully deterministic. Historically, the first time that was really pointed out that physics could be not deterministic at the fundamental level comes with quantum mechanics. This has been a great breakthrough, and people were not wrapping their heads around of how it's possible that we have to abandon the security of our well-established determinism. How does it come about in quantum mechanics? The indeterminism, it comes through mainly two features: Heisenberg's uncertainty principle, that contrarily to what I've showed you in the previous slide, here we have you cannot have in phase space a mathematical and dimensionless point. You cannot be precise as much as you want, but you need to have But quantum mechanics, by its own formalism, by the fact of having the commutation relations between position and momentum, forces to have a finite volume for the states in phase space, and this finite volume is quantified by a new constant of nature, as you all know, the Planck's constant, or the reduced Planck constant. So the volume divided by 2 pi h bar for each degree of freedom gives you the minimal. So this is the minimal amount of volume that the state can occupy. And on top of these, Bell's inequalities show us that under certain assumptions of locality, particularly, the outcomes of distant experiments cannot be predetermined. So you have on top, and also Bell's inequalities, of course, rely on having h bar. So because to violate them, you need to do to take incompatible measurements at the different locations. Good. So this is the kind of the standard story, right? Let me repeat. Classical mechanics, fully understood, a monolithical interpretation that it's deterministic, whereas we know that quantum mechanics surprisingly breaks this comfort of determinism. All right, but then historically, let's look at the right-hand side of this table. What I've showed now is this kind of quantum mechanics, is the textbook quantum mechanics, but there has been, of course, attempts of alternatively interpreting quantum mechanics, and this is successfully done. So you have Bohmian mechanics, as it were, or a pilot wave interpretation of quantum mechanics that adds non-local additional variables and completes the theory to restore a form of determinism. Therefore, quantum mechanics can be interpreted deterministically or indeterministically, depending on the additional variable the one adds by hand. So you have to give it an ontology such that you can restore determinism. And so our question is, can you do the same with classical mechanics? So is it just a historical accident that classical mechanics was always interpreted as a deterministic theory? And it could have been a similar debate also in classical mechanics, because at the epistemological level, what we measure clearly is never infinitely precise. We don't measure real numbers. We measure just as sequences of finite numbers that can approach in certain limit a real number. Okay, so the whole starting point is like, can we investigate what happens in this corner here that seems to have been neglected by science and its history? We start by noticing that in classical physics, there is a unspoken, tacit assumption, which we call principle of infinite precision. So when you open the textbook of classical mechanics, the first page perhaps will tell you that physical systems are characterized by their possessed properties that take value in the real numbers. So there is an ontological assumption here very strong that there exists at any instant of time an actual value of every physical quantity with its infinite predetermined digits in any arbitrary numerical base. This is the principle that is tacitly assumed and we have spelled out here. What would happen if you relax such a principle? So relaxing these principles opens up a new class of alternative and indeterministic interpretations of classical physics. We have substituted this by a principle of finiteness of information density, that a finite volume of space can only contain a finite amount of information. And if you ask what this means, you can compute information, for instance, in terms of Kolmogorov complexity, or you can compute the information in terms of Shannon entropy. And almost all, in a mathematical sense, real numbers are non-computable. So we don't have a constructive algorithm that outputs the real number. So even the typical real number that you have in mind. That might be square root of 2 or pi or e. These numbers are very, very particular. They belong to a subclass of real numbers of measure 0. So they are like, if you pick a random number in any interval with probability 1, you find the number that contains infinite information. It has infinite Kolmogorov complexity. You cannot predict what the next digit of the number will be. So what happens if you instead substitute this infinite precise real number by any finite volume, any finite information that goes in a finite volume? So in this case, in this alternative interpretation, the initial conditions are not anymore real numbers. So you have a certain amount that you can decide, as long as it's an arbitrary amount, but you can you have a certain amount of fundamental indeterminacy. So the state is not that is unknown, but we postulate that there is no way to, in principle, to determine the state. Is not determined up to a certain precision, in the same way that you can tell about the quantum state. That is the complete, a pure quantum state is the complete amount of information that is present, that it exists, and this limits its state in phase space. Here you think of the same, and on top of this you have that there is existence of classical chaotic systems, which therefore, if you plug in this any amount of initial indeterminacy, chaotic system let it spread unboundedly. So you can actually transform a very small amount of indeterminacy into an arbitrarily large one, feeding it to a chaotic system and let it evolve. So somehow, if you come back to the picture of the double interpretation, deterministic and indeterministic of quantum mechanics, we know that we have a deterministic completion of the theory in terms of Bohmian initial positions of the particles. And here you can think of the same. You can uncomplete the classical theory by removing its hidden variable. As Gizan said, like one could add supplementary variables to alternative classical mechanics in order to restore determinism. So it is sufficient to add their mathematical real numbers as infinite precision to have back the standard or the orthodox interpretation of classical mechanics. So through a picture, you see that the infinite precision that I've showed you before, as I already said, together with its dynamical laws, leads to complete determinism in classical physics. However, with our assumption of relaxing this unwarranted principle of infinite precision, you have a finite volume, and this, as I told you, resembles very much quantum physics, and therefore indeterminacy in the initial condition can spread as much as you want. Therefore, if you have a particle that starts perhaps in this kind of blob form, this thing can evolve into a much larger portion of phase space, and therefore, if you measure it afterwards, its trajectories are multiple. You go to a fundamentally indeterministic interpretation of classical physics. You have, from the same initial conditions, that if it's not a single point, each point evolves in different trajectories. Therefore, you have a collection of possible futures. Two short remarks about indeterminism in general. So first remark that prevents perhaps some of the criticism that I have received in these years is, okay, but what do you mean that you have indeterminism? We observe all the time. We have harmonic oscillators. You know that physicists are obsessed with harmonic oscillators, clocks, etc. Two-body problem. Okay, there are some systems that are very regular. So what I mean by the existence of in fundamental indeterminism is not that every system, that everything is lawless, everything is irregular. There is, of course, systems that are very deterministic, that you can predict, linear systems that have integrable solutions that you can predict with arbitrary precision, and there is chaotic systems that we are not able at all to predict in very short time spans. So indeterminism, in the words of Popper, merely asserts the existence of at least one event, or perhaps one kind of event, which is not predetermined. So it's a sufficient condition. And the second remark, yes, there is a question.
Yeah.
Please.
So when you give a principle, so it should be applied to any attributes of that theory, right? So when you are saying some principle about classical physics, so any attribute existing at that theory, at that level, should should obey that principle. So like you are saying, some specific system like harmonic oscillator and all, for that, this intrinsic indeterminism which you have assigned in your theory, that is not there. But in some other case in chaotic system, it is there.
No. Which is, yeah. Finish the question, but
yeah. So I'm telling then, for these systematic systems like harmonic oscillator, for example, how do you justify your assumption, like what you have taken beforehand, like in the principle?
Thank you. Yeah, I should clarify this. No, so the principle is general. It's for the whole view of the classical physics. It's not a certain system having determinants and a certain don't. So also for the harmonic oscillator, the initial uncertainty in the state is there, but the fact that the system is integrable and non-chaotic means that if you start with a very small amount, say you have 1 millimeter of uncertain indeterminacy in the initial state, when you let it evolve for how long you want, the state will remain indeterminate of the same amount. You will still have 1 millimeter that spreads around it. So the uncertainty does not grow, but you have it there. Whereas if you have a very chaotic, well, not very, but any chaotic system, that the uncertainty grows in time. So that's the real difference. So somehow an harmonic oscillator remains indeterminate, but this indeterminacy is not very appreciable, because when you do a measurement in the end, if you knew that it was between 0 and 1 millimeter, also your measurement will be between 0 and 1 millimeter of
that indeterminism is not going to change in future.
Exactly. Whereas for chaotic system, this changes as much as you want. Therefore, if you do a measurement and you can have a ball that is in one side or on the other side of a wall, like in a double slit experiment, then you cannot predict anymore if it was here or here if you have a chaotic dynamics. So that's the difference.
Okay, thank you.
Thank you. Okay, so let me go on. And the second remark I had on indeterminism is that indeterminism is kind of all or none, all or nothing. So we know that device-independent formulation of Bell's inequalities show that if the inputs, the measurement settings, are independent, and you have and you pose the constraint of locality, or of no signaling even, like if you cannot communicate between these two settings, and you can be sure that the settings are independent, then Bell tests that violate a Bell inequality, the outcomes cannot have predetermined values. Therefore, you can think of Bell tests as machines that enlarge. Instead of using chaotic system, you can use Bell's violations to enlarge the amount of indeterminacy. Of course, you cannot be sure that the initial inputs were independent. There is like super deterministic theories. So, but if you were able to know that there is one single event that that can be, there is a message. Okay. If there is at least one event that you can be sure that is indeterministic, you can feed it to a Bell, you can use it as an initial input for a Bell inequality and enlarge the amount of indeterminacy. These is a theoretic information theoretic proof of non-predetermination. All right. So, oops. Okay, so let me go into more this potentiality realism, a novel interpretation of physics that can be applied both to quantum and to classical physics. Okay, so if we start now thinking seriously about this possibility that the world might be non-deterministic at any level, including the classical description, this non-deterministic world should be able to produce non-necessary events, new information that was not there before. As this sophisticated animation shows, you have a certain bit of say, an event that can be considered a true random number generator. It can be a spin of something, it can be a coin, which is really a chaotic coin, or it's a non-specified it's non-specified physical system, and you can determine that there is a certain degree of freedom, let's say binary for simplicity, that is not determined until a certain time. So you cannot attribute a decidable statement, is the bit 0 or 1? It doesn't have an answer, is not determined in the universe. There is not, this information is not present in nature. And then there is one moment where this thing triggers and the bit becomes, for instance, j equals 0. So new information is produced. Okay, so this new information might be fully random, might be completely unstructured random. It's a perfectly biased coin, but can also be indeterminate, so remain indeterminate, but have an intrinsic bias to it. It can have well-determined potentialities, and the potentialities can have various strengths. And this is the approach that we're gonna explore now. So, coming back again to the definition of a classical state, a physical state in general, in any realistically interpreted theory, so it's not a state of knowledge, but is the state of properties of a system, is a system's maximal or complete set of intrinsic or possessed properties. As we have already recalled, in standard orthodox physics, both quantum, especially classical, outcomes are manifestations of actual pre-existing determined properties, infinitely precise properties, and a measure that gets unveiled through a measurement. Okay, so the possessed properties is what it actually exists, and then you go to measure it and try to approach with to approximate this knowledge with your knowledge, but this isn't something intrinsically existing. What we have proposed now is that you have a potentiality realism. So we want to have still a realistic account of nature, in the sense that some systems are still characterized by an intrinsic state, so an intrinsic set of properties. However, outcomes now are dynamically realized. They come into existence, generating new information from an array of mutually exclusive potential outcomes. So before the realization of only one of the potential outcomes, the element of reality, the state, is the collection of the potentialities. And we call these potentialities, according to some literature, and propensities. So you have to imagine that systems have objectively existent tendencies of generating a certain outcome if they were to be measured. And now I will go to characterize more what we mean by these potentialities. So we want them, these tendencies should, we want to have a causal structure. In physics, we still want to have the possible, as a fundamental feature of physics, we want to have causality. We want that if I move a system somehow, if I kick a system, this is able to trigger a certain amount of effects, and that this thing can be causally related. We want to have a concept of objectivity, so we want to have that this is the state, is not my knowledge about the state, but it's an intrinsic, objectively existing property, intersubjective to any possible observer or even independent of observers. And we want this to be not governed by necessity. So we really want to explore the indeterministic possibility. Therefore, these potentialities take the form of a propensity, which is something similar to a probability, but I will describe that is not fully a probability in the so its mathematical representation is not fully probability. But you can still write it like as a P of an event A, given its causal conditions, as is written here, is the tendency of an event A to happen, for instance, the outcome of a measurement, given the relevant causal connection that influence the realization of that outcome, for instance, the setting of an idealized measurement. So you have this non-deterministic causal connection, which measures the likelihood of the intrinsic likelihood, and this we take now as a new physical property. So propensities are as necessary in a description of a causal deterministic world as actual possessed properties are necessary to describe the deterministic one. Yes, please. There is a question.
Can you please emphasize the third tendency, because first two tendency I can see that are already existing in the existing hidden variable theories like people propose, the causality and realism. But the is the third one making your this potentialities different? I mean, this new way of thinking realism different. Is the last one making such?
I'm not sure I understand what so
not governed by necessity. This third tendency. So can you please emphasize that? Because first two are anyway, any hidden variable theory should have these tendencies, right? Causality and realism.
Yeah.
But the third one, I'm not sure about it. Whether this third tendency is making your this new definition of realism a different kind.
Well, that's the main thing that makes the new definition of realism of different kind, right? Normally you define things through their possessed actual properties that exist all at once.
Right.
Whereas here the somehow realism has this intrinsic dependency on the time, in the sense that right now there is a certain tendency that will evolve. So it's the outcomes are dynamically realized in this view.
Mm-hmm.
There
like
is
one
not
outcome
like
can occur out of nothing, something like that you want to say. Like
sorry?
Dynamically, when the system is evolved, so outcome can occur out of nothing, right?
This I will discuss in is probably the most important problem that will arise, that I will show in some slides towards the end.
Okay, sure.
So let's say that let's postpone this question if you still have it. I will talk much more.
I will ask later. Okay.
Realities, and later, if it's still unclear, you ask me again. Thanks.
Yeah.
Okay. So let's go to characterize a bit more these propensities that I hope is clear what at the intuitive level, I hope is clear what I want to do with this. You have like this kind of causal relations that are looser than determinism, is a weaker causal relation. So two events are still causally connected, but it means that if one happens, influences the tendency of the other to happen and is not necessarily forcing the other event to happen causally. So the first thing we want to say about these propensities is that they belong to the single case. It's a property of an event or of a set of events, and is not a property of a long run of repetitions, as some other have proposed in the literature. So they are really single cases. It's a causal law that connects single events. It's intrinsic because we want this to the new form of realism. So it's an intrinsic property of a system, and perhaps of its everything that has causally influenced the system in its past. So it's an intrinsic property of a system, quantified tendency to realize a particular idealized measurement outcome when subjected to specific circumstances. And these are the complete set of causally relevant conditions. They are indeterminate. We want them to be indeterministically causal. So they quantify the degree of objective possibility. So one can see them as an indeterministic law or a potential force. And they're real. We postulate propensities an element of reality, like atoms, chairs, ourselves. They exist there, out there. And they are what actually explains the causal connections we see in our experiments, for instance. So this is the interpretation of this potentiality realism. Propensities also allow to think event as actually happening in time. They have this idea that you have a certain list of potentialities in time, causally and indeterministic. So you can draw a causal graph here, and this is actually a multigraph, as you see. Like the nodes are possible events, and you have and the arrows are weighted, you see. So you can have event 4, for instance, that can either evolve into event E5A or E5B. These are two mutually exclusive events. And these two are the two propensities associated with event 4 evolving into either this or this. But as you see, this is a multigraph because there is a past and there is a future of this graph. So what does this mean? It means that certain propensities have evolved into be either 0 or 1. They have actualized. So the way we see things have been determined now means that the certain process has happened that has actualized the propensity into being either 0 or 1. And when this happens, this causes the determination of a certain system, of a certain set of events. Therefore, propensities allow to indirectly define the concept of present. So you can have a manifold that separates the causal subgraph that only contains propensities of 0s and 1s, and the one that contains the open future. So propensities separate past from the future in this way when they actualize. So this really is a concept of becoming that is very explicit. All right, now let's try to characterize them a bit more at the formal level because we want to work with these things. And so propensities, as they have been proposed at the beginning for the first time in the 1950s by Karl Popper, they were considered a new interpretation of probability and still are in the foundations of probability. The objective interpretation of probability is considered to be the propensity interpretation. So you think that your probabilities are not a degree of belief, as Bayesians would say, and are not just a frequency of accumulation of many outcomes, all the successful events over the total events. So it's not a property of the whole sequence, but you think the probabilities are single case objective tendencies. However, this was pointed out by Humphrey, and we have reformulated a bit this paradox. It's called Humphrey's paradox, but you can call it also Humphrey's no-go theorem in the way that I have formulated. That shows that propensities cannot be properly probabilities. And the theorem is very simple. It goes as following. It has two assumptions. Propensities quantify indeterministic causal connections, so they are intrinsic tendencies. And propensities are probabilities that satisfy all Kolmogorov axioms, in particular those from which Bayes' rule is derived. And this is the simplest example that violates this theorem. So you take the Bayes' rule. Now you want to interpret this P of E given C, where E is an effect and C it's its cause. You want to have this object. So let's start from the causality constraint first. So if you have a probability of a cause given its effect, this should be just independent of the effect, right? Because you want to have causality in the picture. You want that an event is affected by its cause non-trivially, but the cause is not affected by the event. You don't have retrocausality. Therefore, you impose this. Now, Bayes' rule, it's a theorem that is derived from the Kolmogorov axioms. And if you plug this into this, you end up that also the event does not depend on the cause. So the symmetry in the argument of conditional probabilities, well, actually of joint probabilities from which you derive the conditional probabilities, does not allow probabilities to be interpreted causally in the same way that we want. Therefore, propensities cannot fulfill the axioms of probability calculus. So propensities are not probabilities. However, they must share a large part of properties with probabilities. Why is this the case? Because we want to have a certain epistemic access to reality, right? And if there is these propensities existing, you want to be able to at least measure them in a certain approximation, in the same way that you measure the actual values in the standard interpretation. So you need to have a certain compatibility with observations in the form of the law of large numbers, of Bernoulli's law. So propensities are constraints from compatibility with observed statistics. They have to, so actually the observed statistics are supposed to be a manifestation of the propensity. When you do statistics and you see approaching a certain value, you're actually measuring in a certain with a certain amount of conditions. So in the IID, independent identical distributed, if you do many times an experiment, you actually approach what is the tendency of this. So you want to have a law of large numbers still in place. And probabilities are built in the same way. They're built to actually satisfy the law of large number. That's the intuition behind probabilities, that you have a way to operationalize them. So both propensities and probabilities still have the law of large numbers. And then, likewise, the probabilities, propensity want to account for certainty and impossibility. So what is certain, so they must be bounded in a finite interval. We usually normalize between 0 and 1. So also propensities would be bound by this. And to be empirically adequate for quantum physics, they also must be non-local. You cannot factorize the propensities in the same way you cannot factorize the probabilities because of Bell theorem. So in the literature, mathematician Don Gillis has proposed to call propensities a form of non-Kolmogorovian probabilities by analogy with the non-Euclidean geometry. So they are almost probabilities because they have many of the at least operational features of probabilities, but at the formal level, you cannot have a Bayes rule if you want to uphold causality. And I quickly show you this a model actually of what I was telling you at the beginning of this alternative interpretation of classical physics, where you substitute the real numbers with the finite information quantities. That is now the new mathematical entity and set from which the physical variables are supposed to take values. And we define a propensity as a rational number such that it has always finite information. It contains only finite information between 0 and 1. that quantifies the disposition of a binary digit to take the value 1, for instance. So if take a physical variable and write it down into its binary expansion, and each bit then has a propensity associated that tells you whether this bit will be 0 or 1. If the propensity is 1, it will be 1. If the propensity is 0, it will be 0. And then you have intermediate values. If the propensity is 1/2, it means you have an intrinsic chance to have either 0 or 1. And so you can, for instance, have a physical quantity Q, which is now a finite information quantity. And the state is now an ordered string of propensities such that the total information content is always finite. And this was like the first indeterministic alternative interpretation. I call it interpretation in the same, it's a model, it's a mathematical model, but I call it interpretation because it's interpretation in the same sense that quantum interpretations are. So it uses this, it doesn't change the dynamics, it has the same set of dynamical laws. It's just changing the way one formalizes the initial states, and this has philosophical consequences on the whole theory, because it renders classical mechanics indeterministic and still leave all the possibilities of the theory unchanged, in the sense of all the predictions are the same. So one can argue that there is actually room, and we have shown this explicitly in the same way that Bohm did for quantum mechanics, to show explicitly a model where how you can have an indeterministic completion, a deterministic completion of quantum mechanics. We showed an indeterministic incompletion of classical physics. So we have this corner now is spelled out. And now let me get to perhaps the most interesting problem that this opens up, that is related to the question I received before. One at this point has to notice that if there is really this kind of intrinsic and dynamically realized uncertainty that changes in time, as I'm advocating here, one necessarily has a measurement problem. So you know that in quantum mechanics, this is probably the deepest open problem of physics, of how measurements from a superposition, how they carry out only one outcome. You can even negate that this happens if you take a very extreme exotic interpretation, like many words interpretation, that negates that we actually observe a single outcome, but it's the word that splits according to this. I don't want to go in that direction, obviously, but so if we take reasonable assumptions that what we observe is real and we are not splitting into infinitely many words every time we measure a photon, we have to account for why, how, when, under what circumstances the single potential outcome becomes actual. So this is the measurement problem in terms of an actualization problem. Why from an array of mutually exclusive outcomes, one is realized. So why is probably the wrong question, because you don't want to, you want to have an actually indeterministic. There is no why, is you just have this tendency. But you want to know how, when. You want to know if there is a mechanism that does this. And of course, you have certain tenets of measurement that you want to still have in place, right? So you want to have a stability, in the sense that if I take a ruler and I measure a table up to centimeters, I want that if I go there and measure many times, this is not changing. So once you have measured, somehow if this digit was not determined, it must have collapsed in a certain sense. So up to the centimeter length, the table should not change, because we know that there is this stability. You can measure it many times. It should be intersubjective, that any independent of the observer, you want always to have somebody finding that is length x up to centimeter. And then you want, most importantly, precision in probability, because we know that if I measure a new digit, so if I go to the precision of millimeters, so if I couple another measurement system which is more precise, this must force another digit to actualize if this was not yet 0, 1. And so this really imposes to have a measurement problem. And I will now draw a comparison between the measurement problem in quantum mechanics and in this classical indeterministic theory. So different interpretations of quantum mechanics are actually primarily divided about how to explain this process of measurement. You have a Copenhagen interpretation that tells you that you need to have a classical counterpart, so you need a classical system that is coupled to a quantum system, and when this coupling happens, the classical word forces, so you have a sort of top-down, you need another description of reality that imposes the lower description of reality to collapse. And they say you can think of this in my classical indeterminism. You take a better ruler, which is the ruler lies outside. For some non-specified mechanism, you can have a certain kind of top-down. You have a different level of description. Different level means that you have something that is more determined. And when something more determined is put in a certain kind of contact with something that is less determined, it forces it to be determined up to the same precision. You can think of an alternative. These are not even theories. There is not even an interpretation, but a modification of the theory, that the collapse is actually dynamical in the sense that you have a dynamical equation for the collapse. So in quantum mechanics, these are objective collapse theories like Girardi-Rimini-Weber, and they have a nonlinear term in Schrödinger's equation that accounts for the actual spontaneous collapse. And you can think that also in the propensity, there is a mechanism that you have a dynamics that is on top of the classical laws. You have a dynamical law that makes the digits collapse at a certain rate, for instance, and maybe the rate is higher when there is a coupling, like in the Girardi-Rimini-Weber. So you really have a different, this way of thinking of the collapse of digits in the propensities. You have a Bohmian mechanics, so you have a hidden variable completion that we know is the standard classical theory. You add the real numbers, uncomputable, infinite information real numbers, and you have this as a hidden variable. You can even think of a crazy many words interpretation where propensities don't evolve into a single outcome, but they coexist and everything actually happens in different separate words. So many words is not a quantum feature. So
you have
potential.
about 5 more minutes.
I'm done. I think it's the last slide. Thank you. So this leads to the question, what is really quantum in quantum foundations, right? So potentiality realism brings closer together quantum and classical physics, because both can be interpreted indeterministically in terms of these intrinsic tendencies. And this is a very economic way of, it's a very economic ontology, because what we observe in our world, what we always have observed is statistics, right? Even if at the classical level, we claim that this thing is long x, this thing is actually long x with a certain Gaussian that you have collected statistics for. So why don't we accept that this statistics is a manifestation of some intrinsic indeterminacy that we have? I see it as a very conservative way of looking at things. It comes directly from the intuition that what we observe has a bearing in the world out there. So quantum, coming back to why it's interesting for this conference, I've talked a lot about classical physics, but I think that we can understand something from the problems of classical physics. We can turn them into to understand something more about characterizing quantum problems. Fundamental indeterminism is not a unique feature of quantum physics. it's something that quantum physics has, but much more characterized than it's quantified by the indeterminacy in quantum mechanics is quantified by a new constant of nature, h, which we don't have in classical physics, but both of them can be interpreted indeterministically. The measurement problem is not a unique problem of quantum mechanics, and a plurality of interpretation coming from this measurement problem is not uniquely quantum mechanics. Incompatible measurements are the unique feature of quantum mechanics, and the violation of Bell's inequalities also requires them. Therefore, somehow h, Planck constant, remains the unique feature that separates quantum mechanics at the fundamental level from classical one. Thank you very much. And
Thank you, Dr. Del Santo, for a really interesting take on our usual concepts of classical and quantum mechanics. So are there any questions? Okay, we have one raised hand. Shumi?
Yeah, thank you, Professor Santo, for giving such a illuminating talk. So I have just one small doubt. Maybe I have missed something. So like you were saying, so indeterminism, it can, I mean, in any theory, you can assume indeterminism like you defined one. So, and also indeterminism in a theory where indeterminism is defined like that, measurement problem will exist. So by this logic you are saying, so this measurement problem and these things are not unique feature to quantum mechanics. So in any theory where this kind of indeterminism is there, so measurement problem will arise. But assuming such indeterminism in terms of these propensities, where these events are actually dynamically guided by something, right? As the system evolved. So so how do you assure that this intrinsic indeterminacy is not a cause of incompatibility between some observables in that theory? Then it
in
will
the classic,
go back. Yeah,
in the classical case, I mean, of this last feature here.
Yes. I'm saying that the last one, how do you assure that the last one do not imply the first?
Right.
No.
Yeah. Thank you for the question. No, you don't assure this. So it's possible. It's possible that there is some classical incompatibility as well. So somehow, what I'm saying is that explicitly, at least in the alternative in the model of alternative interpretation that I have shown, there is no incompatible variables. So you can still keep all the variables compatible at the same time, but because you have you don't put a hard bound on the size of the smallest cell of phase space as quantum mechanics does. If you would put some constant of nature, but if you would put some constant of nature, this thing would be measurable, would have consequences on at the empirical level. You could propose some tests for this and somehow I guess that the test will tell you that this is h, that this constant is actually h, and you kind of find again quantum mechanics starting from classical mechanics. So I mean, our model is
in the theory, what you are I mean, in the experiment you are telling about, so test this thing, like then I have to assure that there will be a fundamental indeterminacy, but I have to satisfy the incompatibility, right, in that test. Unless somehow I have to satisfy the incompatibility, like I don't know how will be the experimental realization, but while testing it, so I have to satisfy compatibility. I have to have compatible things in that theory, and then I will just test whether there is a fundamental indeterminism.
Yes, if you have an incompatibility, you can do the tests in the same way of quantum mechanics does the test for P and X. But yeah, I mean, it's a good. Thanks for your question. It's a good question. If one can push even further this project and try to, so I don't have a certain answer here, but let's say for the moment, what I have been able to show somehow is that these three features that if you read in the textbook, it seems like the main features of quantum mechanics, this measurement probe and this indeterminism, is it. I just wanted to show the conceptual level that they were all there all along. It's just that we have been well, very good at agreeing in classical physics, and maybe that they're not as necessary in classical physics. I'm not claiming that we should revolutionize anything, but I'm just claiming that as a proof of principle, you can actually have a fully developed interpretation of classical physics that has the same problem of quantum. Whether you can go also in the more in the incompatibility, it's an open question, and it would be very interesting to know. Thanks.
Thank you.
Any further questions?
Yeah, can I ask a question?
Yes, please.
Thank you for your talk. I have one question for my clarification. If Hamiltonian of a system is conserved, I mean the energy, I can find mean number of photons and noise over time for given initial conditions. So graph of mean photon numbers and noise will show the same behavior over time if I will run my calculations again and again. So my question is, so in this case, will I see quantum indeterminism, or where I can see the quantum indeterminism is present?
Will you see if quantum indeterminism is present from the average number?
Yes, because if I will run my calculations again and again, I will see the same behavior of mean number of photons and noise. So in this case, two questions: will I see quantum indeterminism, or where it is present?
Well, I mean, you will see some indeterminism, right? The nature of this indeterminism is not clear, and even like you will surely see the same distribution, more or less. No, if you have like the independent, if you have identically distributed initial conditions and you can certify these, for sure you will have a collective behavior that is the same. But for certainly you will have noise, as you said, and the noise will change, will have the same shape, but will, if you take the distribution in terms of bits of this noise, will be different. So I think that at the practical level, there is no way to tell apart what is the source of the noise that you see. It could be just really noise. It could be like a problem of not perfection of the apparatus, but it could also be that it's measuring something that is at the fundamental level oscillating. So what I want to say somehow is that, and this maybe is a bit dissatisfactory, but there is no way to actually measure the source of this indeterminacy. We only observe that there is something changing in every experimental run, but to trace down trace back the source of this indeterminacy, I don't have an idea how to do it.
Thank you.
Okay, so if there are no further questions, we thank the speaker once again. Thank you, Dr. Del Santo.
Thank you very much again for this invitation.
Yeah, thank you for your nice talk. Perhaps you can stop sharing and
yeah, sure.
Yeah,
good.
Thank you.
Have a good day.
Yeah,
Thank you.
You too. Bye. Okay. So Professor Harshvardhan Vanare, I did see you in the participant.
Yes, I'm.
Okay.
I'm around. Yes. Can you see my camera? Not yet.
Not yet. No.
Yeah. Yes. Yes. I'm around. Yes. Hello.
Yeah. Nice to have you with us.
Thank you very much. Yes.
So our next speaker is Professor Harshvardhan Manare. He's an associate professor at the Department of Physics and Center after a very philosophical one. So the floor is all yours.
Yeah, thank